Welcome back to Easy Academic. Today in the linear algebra series, we're going to be going over the topic of the dot product. So the dot product of two vectors, let's say vector A and vector B, is denoted as A dot B. And so what this means algebraically, let's say A is a vector in two dimensions. Let's say it has entries A1, A2. And let's say B similarly has entries B1, B2. If we took the dot product of A dot B, which would look something like this, what, what we'd be doing is we'd be taking A1, multiplying it by B1, and then adding A2 multiplied by B2. And so what we'd have is A1 B1 plus A2 B2. And as you might imagine, for higher dimensions, this trend would continue. So let's use an example in 3 dimensions to illustrate this point. Let's say we have matrix A, which is equal to, let's say it's equal to 2, -1, 3. Let's say we have matrix B, and we'll set that equal to 4, 0, -2. If we took A dot B, which is equal to 2, -1, 3 dot 4, 0, -2, what we'd find is we'd first take the first entries, 2 and 4, multiply them, add the second entries, -1 and 0, and then add the third entries 3 times -2. So what we'd have is 2 times 4 plus the second entries, -1 times 0, plus the third entries, 3 times -2. And so what we'd find is that A dot B is equal to 8 plus 0 minus 6, which is equal to 2. Let's now take another example where we'll set A equal to 1, 2, and we'll set B equal to 2, -1. So if we now attempted to take A dot B, which would be equal to 1, 2 dot 2, -1, what we'd obtain, and you can pause the video here to attempt to do the question yourself, but if you're interested in just seeing the answer, what we'd obtain is 2 times 1 plus 2 times -1. And the order in which you multiply them doesn't really matter, because multiplication is commutative. We'd find that this is equal to 2 plus -1. Sorry, -2. We'd find that this is equal to 2 plus -2, which is just 0. And so this is an interesting property that we can deduce from dot products, is that when we have two vectors whose dot product is 0, that means that the two vectors are orthogonal. Orthogonality basically refers to any two vectors who are perfectly perpendicular to one another in 2 dimensions or in 3 dimensions. So that means in 2D or 3D, these two vectors are separated by 90 degrees from one another. To further incorporate this idea of angles, let's introduce the concept of cosine similarity. So cosine similarity is given by this formula. So cosine similarity is given by the formula cosine of the angle theta, and where theta is the angle between vector A and vector B. So cosine of the angle theta is given by A dot B divided by the magnitude of A times the magnitude of B. So you can feel free to attempt to find the cosine theta of the angles between A and B. So if you'll remember from episode 1 of the linear algebra series, we can obtain the magnitudes of A and B using Pythagorean theorem. So first we'll find the magnitude of A. We know that magnitude of A is equal to the square root of 1 squared plus 2 squared, which is equal to square root of 5. And we know that the magnitude of B is equal to the square root of 2 squared plus negative 1 squared, which is equal also to the square root of 5. So, if we now take the dot product of the two vectors, we already know that this is equal to 0. So we know that cosine theta is equal to 0 over root 5 times root 5. So it's just 0 over 5, or 0. And as we know, since these two angles are orthogonal to one another, as we earlier established that dot product of 0 indicates orthogonality, this means that cosine of theta equals to 0. And we know that this occurs at 2 points in the unit circle. We know that this occurs when theta is equal to 90 degrees and when theta is equal to negative 90 degrees, or 270 degrees. And so this proves that two vectors are orthogonal, or that they have a 90-degree angle between one another, when their dot product is 0. Because since the numerator is always going to be 0, that means cosine of theta equals 0, and that has to be one of these two angles. If you have any questions, feel free to leave them in the comments below. Make sure to like and subscribe for more future videos on linear algebra, and thank you.